So in this video, I'm going to define the conjugate of tangent z. So the input for tangent, the conjugate of that, where z is in complex numbers. And as a bonus at the end, I'm going to derive the sum rule for tangent, which works for both complex analysis and real analysis. So first of all, let's jump into the complex analysis version of this. And there's many ways you could write this. And the way I've got at the end is slightly different to what you would see in textbooks, but then the one at the end you'll probably be more familiar with. So I'm going to derive how to do that. So the conjugate of z. Well, first of all, we're dealing in complex analysis. So if we define z as x plus I, y. So all complex numbers can be defined like that. For x and y is then in real numbers. So x and y, they are in real numbers. So I gives us our imaginary part. Okay, now conjugate of z. So the conjugate of z, with this as our input, that just means we change the sign of in between the real part and the imaginary part. So x minus I, y. So in this case, that's the conjugate of that input. So with that in mind, I'm going to rewrite my tangent of z, conjugate z. So now let's start this over here. So tangent of conjugate z, we can rewrite that as tangent of x minus iy. And that's all legitimate and that's fine. Okay, so what can I do now? I've got two inputs for my tangent. So what I can do now is perhaps use the sum rule. But the sum rule for tangent, I don't want to go down that route in this video. Why don't we go down the sum rule with sine and cosine? Because obviously tangent z, that is simply sine of z over cosine of z. Nothing crazy there. But in complex analysis with the conjugate, tangent of conjugate z is the sine of the conjugate of z over the cosine of the conjugate z. And that's where we're going to go to try and define this in this video. So let's rewrite our tangent of conjugate z. So now we've got sine of conjugate z over cosine conjugate z, which using our input for the conjugate, we've now got x minus iy. So I've got sine of x minus iy over cosine of x minus iy. Okay, so that's all good. That's a great start to make. Now what we will need to do now is define our sum rule for sine and cosine. So let's do that on this board. So the sum rule for sine and cosine. So let's say I've got two complex numbers, z1 and z2. So in this case, my z1 would be x and my z2 would be minus iy. So this is then defined as sine of z1 cosine of z2 plus or minus, depending on what the sign is. In this case, we've got a minus sign, so that would then give us a minus in here. So cosine z1, sine z1 cosine z2 plus or minus sine of z2 and cosine of z1. So that's our sum rule for z1 and z2. Now in this case, as I said, z1 would be equal x and z2 will equal minus iy. So it's going to be a little bit to deal with there. Now let's have a look at the cosine sum rule. So we've got cosine of x minus iy. So again, let's define that for z1 and z2. So I've got cosine of z1 plus z2. Okay, so this one's slightly different, but it goes along the same kind of theme. So now we've got cosine of z1 cosine of z2. This time, instead of plus or minus, we have minus plus. So that means we then change the sign of of what we have for our input. So with a minus, we're going to use the plus. And then I've got sine of Z1, sine of Z2. So these are all multiplied, and then with the minus or plus in the middle. And the same here, this is my definition of my Z1 and Z2. So let's wait no more. Let's go straight in our input here for our sine. So there's our identity. So let's just give us a bit of space. So now, sine Z1, cosine Z2. That's our identity for this. So Z1 is X, Z2 is minus IY. So I've got sine of X, cosine of minus IY. That takes care of that. And then I've still got more to do. So as I've got a minus, I now subtract. And then I've got sine of Z2, cosine Z1. So sine of Z2, sine of minus IY. And cosine of X. So that takes care of that. So that's the sine part taken care of. Now we need the cosine. So let's plug our cosine values in. Cosine Z1 and Z2. So that's cosine of X, cosine of minus IY. And then just check our sine. As we've got a minus input, we'll need the plus version. So now we've got plus, and then sine of Z1 and sine of Z2. So now we've got sine of X, sine of minus IY. And that's our setup. So that's all good. Now what we can do is, I'm going to leave this here as our main identity. So I'm just going to leave that with a couple of arrows on it. I'm going to keep that on the board for when we come to our real version. Now I know it looks a bit weird with this minus IY, but you'll see what will happen later. So what am I going to do here now? Well, now I need some more complex identities for trig. So I've got sine of X, cosine of X, that's fine. Sine of minus IY I need to do something with, and this cosine of minus IY. So I've got those turning up in my fraction here. So first of all, let's deal with sine of minus IY. So let's put that on here. Sine of minus IY. So what can we do with that? Now, you can bring this I out and turn it into sinh. So now I've got I sinh of minus y. So that's what I've got there. I don't need that bracket there. I'll just leave that as, take it out. So I've got I of sinh of minus y. Now what I can do now with that, as it's inside and it's for sinh, I can now bring that minus out. So that now equals minus I sinh of y. So I've got no minus sign in there. So that takes care of the sine. Now let's have a look at the cosine. So cosine of minus IY. Where does that take me? Well, as I've got cosine of minus IY, I can turn that into cosh and I lose the I. So now I've got cosh of minus y. So that takes care of that. And as it's cosh, and I've got minus on the input, I can now just lose that minus because they're both the same. Cosh of minus y is the same as cosh of y. So that equals cosh of y. So now I can plug those values into this and replace. So I've got hyperbolic trig functions and normal trig functions mixed together. And that's what I kind of like in complex analysis. I think that's where it belongs. So now let's rewrite these down with their identities. So sine of x, no problem. Cosine of I minus IY is cosh of y. So that's cosh of y. And then I've got minus sine of minus IY is minus I sinh y. So now I'm going to just write that in a bracket. Minus I sinh y and cosine x. So nothing to do with the cosine x, just leave it as it is. Okay, just need an extra bracket just to make that all good. Okay, now deal with this, cosine of x. Now, what happened with the cosine of minus IY? That just turned into cosh of y. So that can just stay there as well. So now something's happening here, which is looking good, but I've got a positive sign in my denominator. So I've got to be careful with my algebra here. So sine of x and sine of minus iy, that becomes minus I sinh y. So I'm going to put that in one bracket. Sinh, let's just tidy that up a little bit. Minus I sinh of y. Okay, actually I only need one bracket. Okay, right, that takes care of, actually I'll put this, no, I do need the second one. So I'm going to take care of that now. So what can I do from there? Well, I'm kind of dealing with tangent, so ideally my answer should involve tangent or even tangent or hyperbolic tangent. So I've got sine of x, I've got cosh of y. I've got cosine of x, I've got cosh of y. So something there matches to give me a tangent, but obviously I can't do nothing with this plus sign. And I've got minus I sinh of y. I could bring this minus I out and turn that to a plus. That would be fully legitimate. Same with here, I've got a minus here, bring that to a minus, then I bring the I to the front and multiply it all by I. That would also be legitimate. So I can do all that in one go. And then that would leave me with cosine over sine again. So with cosine and sinh, this time I've got sine and sinh. So thinking about the normal tangent identity for the double angle, I'm going to use cosine of x, cosh of y. So if I just write this down here, cosine of x, cosh of y. Now what I'm going to do now is divide every term by that, because some of these will disappear into one, some will give me a tangent value. So let's go through it. So I'm going to divide everybody by this. Okay, so sine of x, cosh of y, divide it by this. Well, the coshes will cancel out. Then I'm left with sine over cosine, which will leave me with tangent, which is ideal. That's where I want it to be. So now I've got tangent of x. So that's the first part of my numerator. Let's continue on with the fraction. Then let's deal with this imaginary part. I've got minus I. So let's just leave that as positive I. So plus I. So that's what I like in my complex analysis identities, if I can get that. Then I've got sinh of y, cosine of x. Well, if I divide that by this, the cosines will cancel out. But then I'll have sinh divided by cosh, which is tang. So I've got then tang of y. So I'll just leave that as that. Okay, now what about this one? Well, if I'm going to divide that one by that, that's just going to turn into 1. And then I've got sine of x here, nothing to do with that. Something good will happen when I divide by cosine. But I've got this minus I and plus, so I'm going to write minus I first. So change this plus to a minus. So let's get that off the board. And minus I. Now let's divide this. So cosine x, so sine of x divided by cosine of x. That's going to leave me with tangent. So I've got tangent of x. Tangent of x. Now this is all going to be multiplied by I. So I don't really need a bracket, but I'm going to put one in there anyway. So if I put a bracket there, and then I've got sinh of y divided by cosh of y, that's also going to leave me with tang of y. Okay, so what I'm going to do now, I'm going to rewrite this in a much more interesting way on here. So I'm going to take this off the board and rewrite this in a much more interesting complex analysis way. Okay, right, now let's rewrite this. So now I've got tangent of the complex conjugate of z. And this has been a much more aesthetic way and better to look at solution to our defining this complex conjugate. So now, if I rewrite this, so tangent of x, what is x? X is the real part of z. So I can rewrite this as tangent of the real part of z plus I, and then it's hyperbolic tangent. This time I've got y, y is the imaginary part of z. So now I can write that as an imaginary z. And then dividing that by 1 minus I, I can rewrite that, that's fine. 1 minus I. And then I've got tan and x and y, and they are real z and imaginary z. So now I've got I times tangent of real z, hyperbolic tangent of imaginary part of z. So that, we'll keep that separate to all of this. Okay, right. Now, that I think is a nice way of looking at the complex conjugate of the tangent function. Now, I said what I said at the beginning. I would use this to find the sum rule for the tangent function in real analysis. So let me take this off the board and then we'll go with that from this stage here. Okay, so I've now transferred this into real analysis. So now z equals x minus y. So now we've got to go back to real analysis. So z is a real number this time. So notice the i's this time not invited into real analysis. So I've redefined my z equals x minus y as we did here for our conjugate. So tangent of z is tangent of x minus y as z equals x minus y. So I've rewritten where we got to on that stage. So sine of x cosine y, using the sum rules, using real analysis, and then I've got cosine x cosine y plus sine x sine y. So what can we do here? Now remember last time I divided through by this term here on the bottom left of our denominator. So we do the same again. So divide cosine x cosine y. So we divide every term by that, and that's legitimate. We're not changing the value of anything. So now we get, divide this by cosine x cosine y, sine x over cosine x, we get tangent. And then cosine y divided by cosine y, we get 1. So that's just going to be left as just nothing to write. Cosine x divided by cosine x, again that becomes a 1, so that can disappear. And then we've got sine y divided by cosine y. So that's going to give me tangent y. So that gives me our numerator taken care of. Notice we've got the minus sign in here. If I had a plus sign here, then I'd just flip the signs. Then I've got cosine x cosine y divided by itself. That's just going to give me 1. Then I've got a plus sign here. Now I've got sine x sine y divided by cosine x cosine y. That's simply going to give me tangent x tangent y. So tangent x times tangent y. And that takes care of that. And that's our sum rule for tangent. So with one look at complex analysis, we've made a nice identity for version of tangent and a nice identity here in real analysis just by using some of our working. So that's the sum rule for tangent. Okay.